Hello everybody, and welcome back to the Thermodynamics lecture series by Engineer Tomorrow. So today the topic of conversation is going to be the types of energy that are often seen in thermodynamic analysis. These types of energies include, kinetic energy, potential energy, internal energy, and these we'll be discussing throughout this video. So first of all, I wanted to talk a little bit about energy and the forms in which it exists. So energy is typically found in, there's thermal energies, there are mechanical energies, there are kinetic energy, which I'll say is Ke, potential energies, there are, electric. So when you produce a certain amount of electricity, there's energy potential in that. There are magnetic energies. There are nuclear and chemical energies. And there may be more which I'm missing on this list, but you get the point. There's a lot of different kinds of energy. In this thermodynamic analysis, or that thermodynamic series, I guess, we're probably going to be focused mainly on the thermal and mechanical energies and the kinetic energies and potential energies. Although with our analysis we could, apply that to the electrical, magnetic, nuclear, chemical. But more than likely we won't be looking at maybe any electrical analysis. Maybe we'll just say that a generator produces a certain amount of work for our system, or there's a certain magnetic amount of heat or magnetic work that is being induced. There's nuclear heat being applied to our system. So we'll mainly identify that in these four terms. So we'll use a lot. So these are the main ones that we are going to be focusing on throughout these videos. Okay, and just to get a feel for what energy is, so energy is typically written as E if it is on a mass basis. So this is typically seen in joules. Okay, and a joule is a Newton meter. So if you think back to physics, this is like your force times your displacement. Okay, and that's usually how I think about these units. I just think, okay, how does this relate to the more fundamental concepts like force or displacement or time and things like that? And it gives me a good idea if, my units are correct, if I'm doing analysis and things like that. So there's also a different form which things are typically written in, and it's this lowercase e, and this is essentially the energy, which you see up here, divided by the mass. So usually per mass basis is used so that you can apply the process to something else with, a higher concentration of mass. So like what happens if I put more mass into my system? How does that going to relate to my energy? And that's typically why these lowercase variables are actually used. And if you go ahead and look in the back of the book, or a back of a thermodynamics book, I'm not assuming you have any thermodynamics books with you, they're typically written, so internal energy will be written as a lowercase u. There's something called enthalpy, which we will be discussing later, which is lowercase h. There's also lowercase s, which is entropy, which we'll talk about definitely later, and how it applies to the second law of thermodynamics. There's specific volume, pressure. Well, I guess pressure and temperature aren't really in lowercase, but basically what I'm trying to get at is that these are in some unit per mass. Okay, and that's just so if you see uppercase, it's on a mass basis. Lowercase, not on a mass basis. So additionally, thermodynamics is usually split up into two sections. There is the macroscopic, I'll say macro, and there's the microscopic. Okay, and the macroscopic you can think of as large external effects. So if you think about like gravity acting on something, okay, some sort of force that's being applied. Those are macroscopic things. It's things you can actually see with your eye. So microscopic, you when we think of microscopic, you got to think of the molecular level. Okay, and on the molecular level, things are not still. Okay, if it was still, the world would be a very cold place. So essentially, you have all these little molecules that are all over the place, and they're just bouncing back and forth. And the way that these are quantified is with internal energy, which is U. So this is internal. Oh, sorry. Internal energy. And this is essentially just a way you can kind of package. Whoa, what just happened? Sorry about that. So basically, internal energy is just a way you can package this up and ship it off to your analysis. Okay, you don't have to worry about how the molecules are behaving, the structure of the molecules, things like that, as long as you know the composition of what's going on over here. So that's the difference between micro and macro, and typically you can take the internal energy to a macro scale by using this internal energy concept. So additionally, I just wanted to identify what the kinetic energy is. So kinetic, which I discussed earlier, or I said earlier was going to be very useful, and that is written as Ke. And kinetic energy is essentially quantifying the energy that is due to motion. Okay, so if you have a pendulum that is swinging and it's moving at a certain velocity, that actually has kinetic energy, and the way you quantify that kinetic energy is Ke is equal to 1/2 the mass of the system times the velocity squared. Okay, and if you do that on a per mass basis, you get v squared over 2. I guess I can do little lowercase k and e. And so once again, I'll take you to the pendulum. So there's 2 scenarios, right? You have the pendulum when it's moving, let's say, let me use a different color. So if the pendulum is swinging, okay, let's see. Let's say you're swinging that way, okay? At the bottom of those points, your velocity is going to be as high as you're going to get it, okay? So at this point, you have the maximum. Man, I got to figure this out. You have the maximum kinetic energy. But what happens when the pendulum gets over here? Okay, at this point you have the maximum amount of potential energy, which is the other one that we were discussing. Potential. There's an I in there, and that is going to be written as Pe. So the potential energy is just another type of energy which is related to the displacement. Okay, so potential energy is quantified as the mass times the gravitational pull. So on Earth it's 9.81, and then times the height. So as you get higher, you're going to have more potential energy. So if you think about, I'm carrying a big boulder above your head and I'm 10 meters high. If I drop that boulder on you, it's going to hurt a lot more than if I dropped it closer to your head. It would still hurt, but it might hurt more if I was higher up. So that value right there, that's your potential energy. So if you look at this pendulum, when it's at the highest point, you can kind of get a feel for how fast you're going to be, your pendulum is going to be moving when it gets to this location based on the displacement in the height direction. So in the y direction, let me just say y. This is x and this is y. Okay, so that's potential energy, and in this pendulum, you can say, your potential energy is equal to your kinetic energy, and I'll be describing this in more detail later on, but basically, you can use your potential energy to determine your kinetic energy at different positions on this pendulum based on the height, where you are from the maximum position. So this up here would be the maximum potential energy you could have. So you would be somewhere in between while this thing is going through, and you can quantify that velocity using energy energy measurements. So, just one more thing, I'll write it up here. Energy is typically, so when we look at energy, we're going to be looking at the change in energy. Okay, so typically what you'll see in engineering analysis is the change in energy. So we're not really interested in, what is the absolute amount of energy that we have in the system. That's more for nuclear applications. So if you're trying to quantify how much energy you can get out of some sort of nuclear reaction, then maybe the absolute energy would be important. But for our practice, we're just going to look at the change in energy. This will allow us to get the work, the work and the energy, or in the Q that we need. Let me just box this away from everything else. The amount of work, the amount of heat that we're going to need for our system, just so that we can determine what we need to get our system to work. Mostly we will not be working with nuclear, so you probably won't have to worry about that. So I just wanted to make that important note, that we're going to be looking at a change in energy, not the absolute value of the energy. And that still allows us to do our analysis as well. So I think that kind of wraps up our, actually no, one more thing. So energy, so let's say you have a closed system. Man, I'm running out of space. Tell you what, I'll provide this in the next video, okay? Thank you guys for joining me. See you in the next video.